Hi, welcome to AP Chemistry. This is Ms. Dahlberg. We are working on some thermochemistry free response questions. And the first question we're looking at right here is from 1984. And we're given some standard heat of formation information, and we are trying to find the enthalpy change for the combustion of butyric acid. And butyric acid is this compound right here. We're given the combustion reaction, and we're given this number right here. They say that the delta H naught of combustion is negative 2,183.5 kilojoules per mole of reaction. And looking at that, we are supposed to calculate the standard heat of formation for butyric acid. So this is this comes from Hess's law, form of Hess's law, and this equation that we can use, you can even find it on your formula sheet. So if you have any reaction whatsoever, if you add up the heats of formation of the products and the reactants, then you can find the heat of formation of those things, or you can find the delta H, the enthalpy of that reaction. And so to set that one up, you would go to the basic equation, the enthalpy, or the standard enthalpy, and that's at standard temperatures, pressures, standard states rather, is the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. And so if you add all of those up and then subtract the two from each other, you can find the enthalpy of reaction. Now if we look at this, for this one, we know the enthalpy of the reaction. But what we're doing is we're looking for one of the reactants. We don't know the standard heat of formation for this reactant. And so if we know everything else, we can look at that. But let's look at the products. We want the sum of the enthalpies of the products. And the products, we have 4 carbon dioxide. So we want 4 times the H naught of carbon dioxide plus we want 4 times the enthalpy of formation of water. These are our 2 products. Okay, now we're going to subtract from that the enthalpy of formation of the reactants. So if we look at our reactants, we have 1, don't really have to write the 1, I'm just writing it so you know, times the enthalpy of formation of our butyric acid. Plus, we have 5 times the enthalpy of formation of any element, 0. Because we're forming that element from the element, and so that's not really any change. There's no reaction, so the value is 0. And so if we come over here, we know delta H for that reaction. It's given to us. It's negative 200 or 2,183.5 kilojoules, and that equals 4 times the delta H naught of CO2, which if we look up here on our chart, this one is right here. We have negative 393.5, down a little bit, plus 4 times the delta H naught of water. And so that one is negative 285.85. Okay, and so we have all of that minus, now minus 1 times the H naught of butyric acid. So I'm going to call that X. That's our X, right? And then plus 0. So in other words, just minus X is all we have right there. And so when we go through and do the math and solve this, we'll have negative 2,000 plus whatever this 4 times this number is, plus whatever 4 times whatever this is, and all of that equals negative X. So the negative that. So when we solve that algebraically, we get X equals, and that's going to be the heat of formation of that butyric acid. So C3, what is that? H7COOH, and that gives us, once we do the math, a negative 533.8 kilojoules. And so this is the heat of formation of our butyric acid. Now, part B says write a correctly balanced equation for the formation of butyric acid from its elements. And so if we start with the butyric acid, the formation of that from its elements, we're going to start with all the things that make it. So the things that form it, we have oxygen, we have hydrogen, and we have carbon. And so if we look at all of those things, carbon, we have 3 atoms of carbon. So if we put a 3, that balances that. If we look at the hydrogens, we have 8 total hydrogens, and we know hydrogen comes as a diatomic element, and so if we have 8 of them, a 4 will balance that. And then lastly, we have our oxygen. Now, oxygen we also know is diatomic, and so if we come over here and we look, there are 2 oxygens there, so our oxygen is already balanced. So there we go. That's that problem. We had 1 point for balance in that reaction. If we jump up here, this part, the points assigned are not clear, but 3 total points for doing this problem. So 4 total from the parts that we've done. Okay, now we're going to after 1984, we're going to 2003, and let's look at that one. We have some liquid heptane is completely combusted to produce okay. All right, let's keep going. Sorry about that. In 2003, we have some heptane combusted. And when it's combusted, it forms carbon dioxide and water. And we're given some values on this table here. And this is asking us if we are given the heat of combustion for 1 mole of our heptane, what is the value for the heat of formation of that heptane? So we know the heat of combustion. What's the value for the heat of formation? And so again, if we set that up, if you are looking at heats of formation or enthalpies of formation, if you start with the enthalpy of a reaction, and this reaction is going to be this combustion reaction right here, and you know that the sum of the enthalpies of formation of all of the products minus the sum of the enthalpies of formation of all of the reactants add up to give you that enthalpy of that overall reaction. That is, like I said, Hess's law. Then you can find that information. Now, putting in what we know from this problem, we know that the delta H is 4.85 times 10 to the third, or 4,850 kilojoules. And let's look at our products. The sum of formation of the products. Now, if we look at our products, our two products are carbon dioxide and water. If we look at carbon dioxide, we have 7 carbon dioxides, and the enthalpy of formation of the carbon dioxide is negative 393.5 plus the other product is water, and we have 8 waters. So we have 8 times negative 285.8. Okay, minus the enthalpy of formation of our reactants. And so if we look at our reactants, we have 2 reactants. We have our heptane, which is our unknown, and the coefficient in front of that is 1. So we have 1 times our unknown plus 11 times 0. If we look over here at oxygen, the enthalpy of formation of any element from itself is 0. And so now we can solve for x. So this term becomes 0. Here we have x, so we have all of this minus x. Solve for x. So when we solve for x, x is our heat of formation or enthalpy of formation of our hexane or heptane, C7H16. And when we add all those numbers up or subtract all those numbers, we get negative 191 kilojoules per mole. So we get 1 point for correct coefficients for those. So 1 point for that, and 1 point for correct substitutions. Okay, the next problem, now we're taking a 0.0108 mole sample, and we're combusting it in a bomb calorimeter, and we want to know how much heat is released to the calorimeter. Okay. And so what we're trying to find, when we're trying to find the amount of heat released, we're trying to find Q. And in this instance, the Q, or the amount of heat released, is going to come from knowing how many moles you have. And so if you start with this many moles of our sample, And you know that when you combust it, you release a certain amount of heat. In fact, when you combust it, if you look at that, if you combust 1 mole of this heptane, you release 4,850 kilojoules of energy. Then you know how much energy is released there. And so if we go through and multiply, you will find out that there is 52.4 kilojoules of heat released, or negative 52.4 kilojoules. Okay, on to the next year. Now we're in 2007. And in 2007, we have this reaction up here. We have nitrogen reacting with fluorine, forming this nitrogen trifluoride, and we're given some information about the enthalpy of formation up here. It says find the standard enthalpy change that occurs when a 0.256 moles 0.256 mole sample of the nitrogen trifluoride is formed. Okay, and so if we look at that, we want to know what that enthalpy change is. So if you have an amount that you start with, a certain number of moles, or it could be given grams, and you could convert it to moles, but if you know the number of moles, and you know in that reaction how many kilojoules of heat per mole are released, well, then you know how much heat's released. So if we start with trying to find Q, how much heat is released, we start with 0.256 moles of our nitrogen trifluoride. It's going to be kind of a stoichiometrical reaction. So we're doing a little bit of stoichiometry here. If you know this many moles has been formed, and looking at our reaction, this is negative 264 kilojoules per mole of reaction. So what that means is whenever 1 mole of this reacts, or 3 moles of this reacts, or 2 moles of this is formed, then we have negative 263 as our enthalpy value, or 264, sorry, kilojoules are released, and that's what the negative means. And since we're talking about the nitrogen trifluoride, we know that when that's released, 2 moles of this are formed. And so when we multiply those, we get 33.8 kilojoules of energy are released. And so that is the enthalpy change. Okay, next part, part D, the enthalpy change in the reaction is the difference between the energy absorbed in breaking bonds and the reactants and the energy released by bond formation in the products. So how many bonds are formed when 2 moles or 2 molecules of nitrogen trifluoride are produced according to the equation in the box above? Okay, so let's kind of break that one down. If nitrogen reacts, this is the Lewis structure. We have nitrogen triple bonded to a nitrogen, and it's going to react with 3 of these fluorine molecules. Okay, and I'm just going to put, instead of like drawing three of them right now, I'm just going to put a 3 here. So there are 3 of those. Okay, and those react and form 2 of these. Okay, so there's the Lewis structure. Nice review if you are a little bit rusty and just kind of there in case you're not rusty, you just haven't learned it yet. But anyway, looking at this, the other thing I want to add is maybe a little bracket and a 2 here because we have 2 of them. Okay, and so for this one, we want to know how many bonds are formed when 2 molecules of this are produced. So if we look, if we have 2 molecules, each of those molecules has 3 bonds being formed. We have 6 nitrogen fluorine bonds forming. Okay, if we look at the next problem, we're asked about the reaction above, and we're given these bond enthalpies, and we want to calculate the enthalpy of the fluorine-fluorine bond. We want to know what is the enthalpy of that bond. So to figure that out, we know the enthalpy of a reaction comes from knowing sum of the bonds broken, or I guess the bond energies of the bonds broken minus the sum of the bond energies for the bonds formed. So looking at that, all of the bonds broken, the values that we're going to use from the bond energy table, they don't really tell us this, but we need positive numbers. That's why it's written like that, because it requires energy to put into the system. And then when the bonds are formed, those are going to be negative numbers because that is energy that's released. And so that's what that negative means. It's released. So if we come over here, actually we could put in the number. This is one of the things that we know. If we scroll up back to that original reaction, we know the enthalpy of reaction. We know that that is negative 264 kilojoules. And so that was given to us right here in this reaction before we even started this part down here. And that equals the sum of the bonds broken minus the sum of the bonds formed. So let's look at all the different bonds that are broken and formed. Now, in the reactants is where we're breaking the bonds. And so if we look at that, we have 1 bond broken. And so the bond energy of the nitrogen triple bond, so that's 1 bond broken. We'll put that in brackets. The bond energy of the other thing that's being broken, or the other bonds that are being broken there, are the fluorine bonds. And if we look at that, we have 3 of them. So we have 3 of these fluorine bonds. So Now, that's going to be positive. All the bonds that we're forming now are going to be negative. And if we look at that, we only have one kind of bond being formed in the products. And we have six of those. We have six of those bonds being formed. And we have six of the nitrogen fluorine bonds being formed. And so we put that in there. Now we can plug in some numbers as we look those up. So this is the bond, the enthalpy of that overall reaction. Let's look at the bond energy in the nitrogen bond. So the nitrogen triple bond, nitrogen-nitrogen triple bond, gives us or requires 946 kilojoules. The bond energy of the fluorine-fluorine bond, oh, that's the one we don't know, so we'll call that X. So we have 3 times X, the one we don't know, minus 6 times, now our nitrogen-fluorine bond, we do know that one, and that one is 272 kilojoules. And so now we can solve for X. So when we solve for X, looking at that, the bond energy in a fluorine-fluorine bond equals 141 kilojoules per mole.